Hello, I think quite a lot of people may be interested in this video. I'm going to repair a solar IBoost Plus. Now, I've done another video showing the installation of these and things like the cost benefits, asking the question, is it worth it? I'll link that in. But anyway, thank you very much to Maris for sending this broken unit, and let's get started with the repair. So I've got a bit of test gear on the go. I've got a scope here for later. I'm pretty sure I'm going to need that. I've got high voltage differential probe. The other thing I've got set up is over here is an electric heater, just in the corner of the lab, the corner of my very tidy lab. Just down here, there's an electric heater, so I can use that as a load. So anyway, let's take a quick look and see what's going on with this. This has been already opened. This is Maris. Thank you very much, Maris, for sending this across to me. Oh, there we go. So now the fan should come out. There we go. Just leave that where it belongs. And we'll just do a quick visual inspection before going any further. So over here we've got a little radio receiver, I think. We've got a fuse down here. We'll check that in a second. A lithium ion battery, which has gone a bit wangy. Here's the buttons across here. Here's our LCD display. And that looks like it actually is a proper LCD display as opposed to just a little module, which is kind of what I expected. We've got a PIC microcontroller down here and just a little bit of logic and stuff, and then we've got the high voltage, high current end over here. Now, one of the things I can kind of see immediately is these. Now, someone may, of course, I don't know whether Maris had a repair on this or not, but they're looking not great. That one there looks a very blobby solder joint. Not sure how well that shows up on the video, but yeah, they're not looking wonderful. And of course we've got over here some big diode. There's not a huge amount. There's a little bit of signs of slight warming on the top of the board, but nothing too great. Under the board we've got a lot of inductors, and we should hopefully have some sort of FET or something like that. This looks like it's had some soldering work done on it. Either that or it's got ridiculously hot. Let's just check this fuse first. It looks a bit bendy, to be honest, so maybe as simple as that. So here's our fuse down here. So a couple of T10 self-tappers seem to be all that holds the board in place. There we go. So one just here, and there's another screw over here somewhere, just in the upper board, which also penetrate all the way through the lower board and into the case, just to hold it all together. There's always one. So I'm not going to lose these plastic spacers, because they actually are not spacers at all. They actually are part of the bottom moulding, and they pass right through. These ones here, they pass right through the bottom board and up to the top board. So let's take a look at it underneath now. So on this side we've got a bridge rectifier, that's onto that heatsink, and then we've got what looks like a FET just going onto the heatsink there as well. Live neutral going in. And this is a modular little power supply. It's got 5 volts, 2 watts coming out on 2 of the pins, and 12 volts coming out on another part of it, presumably to activate some relays and stuff like that. So these 2 little wires here. Or maybe it's just a magnetic pickup coming off this coil here, which is a common mode choke, and we've got another common mode choke over this side as well. And another one down here. And we've got a lot of X-rated caps. That's one there. There's another one here and another one here. This is a relay switching output 1. It's output 2 and output 1. So it's simultaneously switching them both. Yeah. I've got to say, some of the soldering on here does kind of leave a little bit to be desired, to be perfectly honest. This bit of copper over here is on the earth strip. It's just reinforcing it. first things first, let's find out about this fuse if I can. I'm going to need a magnifying glass to read that. Okay, so I've soldered on a new fuse holder. I might be able to leave that in, but I don't think I will. I will almost certainly replace it with the same type of fuse. And the reason for that is this, if we get a short circuit, is going to take a lot of welly. And if we put, for example, a glass 20mm fuse in there, then it will literally explode into lots of parts if it gets too overloaded. We definitely don't want that to happen. So I'll need to order a 16 amp fuse, but I'll order the same type that was in here before, and that's a 600 volts 16 amp slow burst fuse, which will have good ceramic cartridge, so that should it blow, it doesn't shatter into pieces. I want to understand whether or not we have a problem that's causing that fuse to blow, or whether it was just a little weird event. So there you go. If I null that, and then we can measure this. It's a 0.3 ohms, so that is a disaster. I mean, that's 250 volts, 240 volts AC, RMS on there. I'll leave you to do the Ohm's law on that, but that's an awful lot of current that shouldn't be present. So, yeah, something else has clearly gone wrong. And let's have a look, and maybe I'll actually trace out for a moment and just actually get the diagram for just the high voltage part, I think, and maybe the initial control bit that just goes before it. Okay, so I've spent a few minutes just sketching this out. Now, I have left off a number of items here, like some of the resistors and capacitors and things like that, and just concentrate on the main flow of high power. So over on the left here, we've got our mains input coming in through the fuse, and we've just got a string here of inductors. So here's a common mode choke, or it's a capacitor, common mode choke, capacitor, common mode choke, capacitor. Just here, we've got a 0.01 ohm current sense resistor with some taps coming off it. And I'm not going to bother with those. Those are going to go to comparator somewhere. And what will be happening is the PIC microchip will be setting a desired amount of current to be flowing, and this sensor will be doing the sending the actual value that is being output. We then get another common mode choke and a pair of capacitors, which are in series. So yeah, I mean that's pretty good, really. So these are higher value than these ones down here. And then we get our bridge rectifier, and our positive from the bridge rectifier goes straight out to the relay, which selects whether it's going to output the positive to either device A or device B, because this thing can drive two different heater elements. So it just goes to a relay and out from the relay to the output. Now the negative comes down, and we've got a IGBT just here, so inside a gate bipolar transistor, and that's actually doing the switching, and it's switching the negative, and so we come out of the IGBT and we go straight out to the element. There is a diode in here across it, reverse diode. That makes complete sense. Actually, I think I've just drawn the wrong way round. Well, anyway, whatever. And there is also a diode between the positive and the negative, which is this big beefy one just here. So coming into the IGBT then, we've got a few little devices down here. So we've got a device here which is marked 3003, which is a ZXGD 3003 E6TA. And what it is, it's a gate driver for IGBTs. So it's designed specifically for that, and it's really got two bipolar transistors inside it. It's a 6-pin device, and what we've got here is we've got an optocoupler on this left-hand side, a 6N136. It's coming through to just a normal bipolar transistor here, a BC857B, for those interested, and then that's going to the base of this higher powered device in here, because this can deliver quite a lot of current, so you need to preamplify before you get to there. So I haven't gone back behind the optocoupler, because pretty much we're going to have some op-amp comparators and a microchip. So let's have a look in here and just think about where we can have current flowing that it shouldn't flow, of course. What could be blowing this fuse? Well, the first, if any of these capacitors have failed, then we will get a short circuit which will blow the fuse, and that's what it's designed to do. Similarly, a fault in our bridge rectifier would also clearly blow the fuse. A fault in this ST3012W big diode here would blow it. I'm less certain about whether the IGBT would blow it. It certainly would if the gate insulation has broken down, because, you know, on the back here we've got a relatively low impedance. I mean, it's not nothing, but it's relatively low impedance. I mean, we've got this is going out to VCC somewhere. This is all referenced to a ground, which is common with our digital circuit and our transfer circuit, this stuff here, after the isolator. So there will be a route through to ground, not necessarily earth, but to some form of grounding through this, which will be a high current route. So it is potential for current to flow, well, actually the other way around, flow through this lot here somewhere. Now, if that's happened, this device is going to be scragged, and probably this, and possibly the optocoupler. Fortunately, the optocoupler has 5 kilovolts of isolation, so there's a good chance we haven't fried the control circuit on the left-hand side of this, and that's why I haven't drawn it. But anyway, those are the key aspects. So I'm going to start off by, I'm going to check this bridge rectifier, I think, to begin with, and I'll start checking across some of these capacitors. I might have to take the bridge rectifier out so that I'm not getting conflicting readings, but I'll see how I get on. Okay, so I'm just testing the bridge rectifier. So this is my AC pin, and I think this is either my positive or my negative. I can't quite remember off the top of my head, so I'm okay with that. I've got a 5.3 volts drop on that, and it's open circuit the other way, so that's nice. Now this is the other AC over here, so this means this must be the other. Oh, so this is negative. Well, that seems to be short to me, and short in the opposite direction as well. So could that literally just be the error? Let's just have a look at this diode. Yeah, that one's okay. Or testing, at least appears to be testing okay using this very simplified test. Keeping in mind this is in circuits. So I'm going to take that bridge rectifier out, I think. So this is a GBPC 3512W. It's a Vichy device, I think, although this isn't not Vichy. And yeah, we can get those. So this is 35 amps at 1.2 kilovolt reverse bias voltage breakdown. The problem with this is there's a 9-month lead time on delivery. I can't find it on any supplier. So if this is fried, then we've got some difficult choices to make. We need identical pinout, but we might have to go for a C3510 instead, or something like that, which has got a 1 kilovolt reverse bias. So we might just have to go for that, and hope that that's okay. Anyway, hopefully my desoldering station is up to temperature. So let's measure between the two ACs. There you go, short circuit. So that is definitely screwed. No doubt about it. So let's come back to here then, in that case, and we'll just measure the resistance between neutral and live again. That looks a bit better. So it would appear that our primary culprit is this guy. Now I'm going to move on and just see if I can just take a little bit of a look at the IGBT for just a second or two, just to see if there's any problem there. Don't forget there's some diodes and things around it, and 6 mega on this one here, and This one should perhaps work one way, and that's an open. 2 meg. Okay, so it kind of looks like that's probably okay, and that we are limited just to this, and that's kind of good news really, because if we come back to our diagram, if literally all that's happened is that this has gone wrong and short-circuited right across between the live and the neutral line, then the chances are that everything else following that is okay. So I've done a quick test on this one, and this is okay as well. So yeah, I'm just going to see if I can find a large value bridge rectifier that I can pop in temporarily, just to see whether the device will operate or not. Okay, so I've inserted a, I think it's a 10 amp fuse temporarily, and a replacement bridge rectifier, although only temporarily. You can see it wired in at the top right there, and connected up the fan, and just giving it a bit of a just a little test. Although the load is wired in, it's not actually switched on, and you can see here it's only drawing apparently 10 watts, but that'll just be a little measurement error. So yeah, pretty happy with that so far. Now I don't have the paired current sensor and sender for this, so I'm just going to switch it on to manual boost, and that's connected to a 1.5 kilowatt load at the moment. I'm not going to leave it on for too long because it's kind of about at the limit of the bridge rectifier that I've got fitted and the fuse that I've got fitted, but that appears to be working absolutely perfectly, and I'll test it for just a little bit longer, and then I'll have to try and source a drop-in replacement bridge rectifier, and it has to be the right pin out and physical size because it's got to fit on the heatsink. So I shall do my best to get hold of something appropriate. Okay, several months have gone by since I started shooting this video, and that's because of trying to get this part. So this is the bridge rectifier that failed. It is a part number GBPC 3512W. So this is, the W stands for wire ended, and the GBPC is the layout. So although this is a fairly normal looking bridge rectifier, let's just switch there so we can see. You can kind of actually see that the pinout is not following the square. These two are closer together. So it's a very peculiar pinout. And this is 35 amps, average RMS, on a fairly constant basis, with a 1.2 kilovolt reverse breakdown voltage. So yeah, we kind of need to get something fairly beefy. So these are available. I found a company, which I'm going to show you on the screen, and they said they had 53 in stock, so I ordered one. And I suppose in fairness to the company, they were fairly quick, a few working days to email me and tell me they didn't actually have them, and it would go on back order, and it would be about 10 days. So that was kind of all right. I left the order open. 10 days later, I had to chase them up, and then it was next month, and then I chased them up again, and then it was another month, and now it's back into November. So in the meantime, I found that RS Online had a fairly short lead time, so I also ordered a couple from them, and they did the same thing. In fact, they kept saying they'd dispatched them, so 9th of June or whatever would be the dispatch date, and on the 9th of June it would show as dispatched, but then I'd look and there'd be no tracking information, so I'd ring their helpline and say, oh no, the date has changed, it's now this date instead. And after 3 times, I've now got lead times running into December 2023, and it's currently July. So yeah, I kind of gave up on that, and I thought, well, the owner of this would probably actually quite like to see at least some of the summer with it working. So what I decided to do instead was to fit this part, and I don't know if you can see there, but it's a GBPC 3510W. So this has got 1000 volts reverse bias. Now, if we do the maths on the bridge rectifier and an AC rectified signal, then we shouldn't be anything like that voltage. The only thing that might happen is if we have an inductive load, we could potentially get larger amounts of just a few spikes, but fingers crossed that won't be the case. And in terms of that switching, in actual fact, this diode just here is there for that purpose. So I think I'm going to fit these, or one of these, and hopefully that will get this up and running and get it back to the person. And should it fail again in the future, hopefully by then I'll be able to get some of the 1.2 kilovolt ones instead of the 1000 volt version. So at the moment I've got this bodge on here. I've got this bodged in fuse as well. I'm going to disconnect both of those and put the proper things in. So here are the fuses, ceramic 600 volt 16 amp PCB mounting fuses. So here we go, let's get the desoldering station up and running and get everything desoldered, and hopefully not very long before we are up and running. And just to make sure it flows properly. We do not want bad connections on this bridge rectifier at all. Lovely, they're looking great. Now we just give it that final tightening push and double check everything is nice and flat on the heatsink, and it certainly does seem to be. It's absolutely lovely. We'll mount it in the bottom of the case and we'll run it up and see what happens. And so assembly is literally just the reverse of disassembly, really. I'm just going to bring the fan into its correct place. Yeah, I'm trying to remember how it fits exactly. There it is. Just buzz out that fuse. Perfect, lovely. There we go, so that's fine. And then we'll connect it live and neutral. And we should have a nice biggish reading. Now, because of course there's capacitance and stuff like that, this reading will gradually drop, but we can see that there's a high impedance there across the mains. So happy with that. So that bridge rectifier is behaving as it should do, really. So next things then is to plug this in. So just check the live and neutral in. There's 241 volts. Check the live and neutral going out. There's basically nothing going on there, and it's saying that the water heating is off. So if I just grab an insulated screwdriver and press that button, insert a bit of tubing and press that button. Lost signal from sender, that's fine. Put the boost on. We get an output of 104 volts. And that's because it'll be AC chopped, which is quite a little interesting thing. So let's have a little look at the signal from that, I think. So I'm going to take a quick look at the waveform, and in order to do that I need one of these differential probes. Because if we think about what's happening here, I've got live and neutral coming in, it's going through a bridge rectifier, and then I'm going to sample over here, which is on 2 DC signals, but those DC signals are not decoupled or isolated in any way from this mains coming in. And on my scope, the outer ring of the BNC, which is the negative connection, is therefore going to be connected directly against the mains. So there will be a direct route from the mains through the bridge rectifier and through the ground of the scope back to the protective earth in the building, which will shut off all of the power very, very rapidly in the lab. Okay, so we can kind of see the type of signal that's actually getting generated now. I will try and get a few more of those in there. So there's your boost waveform. Let me just see if it's triggering correctly, if I'm getting some anti-aliasing going on there, but we can definitely see the chopping effect that's going out into the heater there. So essentially this will be turning on, sensing the current, and then slicing it when it thinks it's running over current. So I've got a nice big load connected up at the moment. So there we go, that would appear to be working absolutely fine. So let's press the button a few times and try and persuade the boost to turn off. There we go, boost off, and the signal has gone. But yeah, good repair. So, you know, we did a bit of a teardown. We've had a look at how it's constructed, the parts involved. I also did some reverse engineering. Reverse engineering might be overstating it, but sketching out the kind of basic principles of the high voltage, high current end of the circuit, and reasoning what might have gone wrong to actually blow this fuse over here. This fuse actually was really hard to fit because the wires on the new fuse are really bulky compared to the old one, but they are both 16 volt 600 sorry, 16 amp 600 volt fuses. So anyway, if you did enjoy that repair, don't forget to click on the like button. Feel free to leave some comments, of course, and if you haven't subscribed already, then please do so. If you do subscribe, don't forget you have to click the notification bell, otherwise you won't very often receive notification of new videos, because YouTube will use its algorithm and spread the love around instead of actually sending links to people who have already subscribed. So there we have it. I enjoyed it. Hope you did. I'll see you next time. Take care. Bye.